Okay, so let's do question 3. The first one here says order the compounds with respect to increasing acidity. Now, we have structures, but the reality is we don't really even need to look at the structures for this question because we know the pKa values, and that's what's going to really drive our decision. So we know that the smaller the number, then the more acidic for pKa. And so in our case, we have -9, which is the smallest number, -8, -7, and then 3, which is the greatest number, the largest number. So in terms of increasing, think about it, we're going from least to most acidic. That's what it means to increase, right? From least to most acidic. So that's our goal. And so that means that this is number 1. This is the least acidic, highest number. Then we have number 2, number 3, and number 4. So 4 is the most acidic, and 1 is the least acidic. And again, we didn't even look at the structure, although we'll do that very soon. For this problem, we didn't have to do that. Okay, so here we have sulfuric acid, phosphoric acid, nitric acid, carbonic acid. But again, we could just look at these numbers, right? So again, from least to most acidic. So this is number 1, the largest number. This is number 2. This is number 3. And this is number 4. There you have it. Very simple. I just want you to get used to looking at the chart, or not even looking at the chart, just look at these numbers that are provided and knowing exactly, what the trend is. Okay, so that's number 3. Number 4. Now we're going the opposite direction. So let me just tell you how we would work that. There's a little bit more thinking to this one. Well, I actually, for this problem, probably is not, but generally speaking, when you're provided structures and they want to know the increase in basicity, then you shouldn't assume that these are the bases. So for example, this molecule is the acid form drawn out. They're all in the acid form. Every one of these, even the negative one, okay? Keep that in mind. So if I didn't have numbers to work from, then we would have to do a little bit more evaluation. And in this problem, we don't have to, so I'll hold off on that description until we get to it. We'll see it soon enough. Okay, so in this case, we're just going to look at the numbers, right? So now we're going from least basic to most basic, right? So what we're going to do is look at the numbers. We want the highest number on the right side and the lowest number on the left side. So if this right here, 10.3, is the most acidic, it's the smallest number of these 4, then this is the least basic. So this is number 1, and then this is number, 10.64 is a larger number. So this is number 1. I'm confusing myself. I was right the first time. Okay. So this number is the smallest of all of them. It's the most acidic. So this is the least basic. This is number 2. This is number 3. And this is number 4. So what I'm doing is I'm looking at these numbers. I'm saying, okay, I know that the most acidic is the smallest pKa value here. And the most acidic gives you the weakest base. Remember that? Strong acid becomes weak base. So since 10.3 is the smallest number of this set, then that means that it's the strongest acid, which in turn means it makes the weakest base, right? So the smaller number is going to be the one that makes the weakest base, whereas the largest number is the weakest acid, so it makes the strongest base, conjugate base. So that's why 44 is number 4, okay? But yeah, so actually let me take a step, and since I already mentioned before, what would the conjugates look like? What would the conjugate bases look like for these? Well, for this one, it's CH2 double bond CH, and that's it, one less H. Remember, they all have one less H, so this would be negative because it was neutral. Here it's HC triple bond C negative because it was neutral. Here, the bicarbonate is CO3. It was already -1, but now it's going to become -2, right? -2. And this is going to be CH3 NH. It was NH3 to begin up here, so NH2. Since it was positive to begin, it's neutral as a conjugate base. So these are the conjugate bases that we're dealing with. right? And so what I'm saying to you is that this is the strongest conjugate base, and this is the weakest conjugate base, okay? Because it has the pK value that's lowest as a conjugate acid, right? From the acid form, it's got a lower pK value of all of them. Okay, so think about this for a moment and make sure that you're comfortable. Let's do another set like this. So let's start by talking about the conjugate. Let's do that first. So conjugate base. HCl is Cl minus. Benzoic acid is C6H5COO minus because it was neutral. P-toluene sulfonic acid is CH3 C6H4SO3 minus. It was neutral. Notice how this is neutral, so now it's negative. Neutral, negative, neutral, negative. Okay, and neutral, so negative, H minus. And those are the conjugate bases. So we're trying to figure out increasing strength or increasing conjugate base strength, right? And so what we're going to do is we're going to look at these numbers and again work through the logic from the acid point of view. If it's a strong acid, it's a weak base. So out of all these numbers, this here is the strongest acid, the smallest number, which means its conjugate is the weakest base. This is number 1, the weakest base, okay? And now let's see the next one up, 0.7. That's a strong acid, small number, which means it becomes the next weakest conjugate base. So this is number 2. This is number 3, 4.19, and this is number 4. This here is the strongest base because it has the weakest conjugate acid. So notice what I did. I'm looking at the pKa values. I'm figuring out which one's the smallest number, and that tells me the strongest acid, which means the opposite for the base, the conjugate base, the weakest base. There you have it. So that's how we work this logic. So make sure that you're comfortable with these two problems, okay? It's very important that you understand what we're doing here. All right, and so that wraps up this problem. All right, the next section now is predicting the outcome of an acid-base reaction. So we're going to now use our knowledge of pKa and our knowledge of knowing how to figure out strong and weak acid-base, and we're going to apply it to actual equations. But before we do that, we have to first talk about curved arrows. This is critical. It's paramount that you know this really well because this is going to be throughout the entire semester. And I cannot emphasize how many people, even at the end of Organic 1 or even Organic 2, still get arrows wrong and they lose points on their exam. You have to be comfortable with drawing these arrows, okay? So what we do to draw arrows, curved arrows, is we take, let's say, an atom and it has electrons or whatever this is, and now it's going to go somewhere. We always talk about where electrons are going. That's what we're referring to when we do curved arrows. We're not talking about atoms, not atoms. So let me give you an example, and the way I'll do that is actually a little bit different. I'm going to say, let's say we have H plus and we have A with electrons, okay? So here's my drawing. Now, there are two ways I can explain this to you, and one of them is wrong, but I'm telling you, and I hope it's not you, but people will do this on their test, okay? They will say, well, if H is going to A, then let's draw it this way. H is going to A. That's not true because we're not talking about the atom, the nucleus. We're talking about the electrons, not the actual nucleus or the atom, the label, the symbol. Okay? We're going to actually not do it this way. What we're going to say is that A is going to have its electrons go over to the H. See the difference? So this is the correct way to do it. You say where the electrons are, that's where you begin your arrow, your arrow diagram, and you show where it's going. Now, notice that there are 2 electrons here, 1, 2.